All right. So this next presentation comes from the College of Medicine, Dr. Adarsh Kumar, and he's going to be speaking on watching molecules in action, time-resolved crystallography. Adarsh, go right ahead.
Thank you, Debbie. This is our DNA, our genes, something which carries information from us to our sons and daughters. And it is under constant attack from several factors: radiation, smoking, pollution, and several internal metabolism and chemical exposures, and so on. Now, when this attack happens, there is always some sort of error, and we have to fix that error if we have to survive. Now, imagine that you have a car with a broken wheel, let's say. It is equivalent to the DNA with the error. Now, in order to fix this, you may need to place a new tire. And here, we have to remove this bad nucleotide, and we have to add a correct nucleotide. Now, if you're a handyman, you could probably do it yourself. But to fix your car, you may have to go to a mechanic. Our body also has several mechanisms to take care of these things. One of them is a human DNA polymerase beta. It is part of a series of enzymes which are responsible for single nucleotide repair. Now, to fix this tire, you need to remove it, which would be equivalent to removal of the bad nucleotide. Put a new tire in. Similarly, some enzyme has to put a new nucleotide in, and then it is fixed. Now, where is the problem? What we're trying to do? If we talk about the tire, we know there we can see the nut and bolts, the axle, the tire itself, and the whole assembly. But when it comes to our body, our internal proteins and enzymes, we are not able to see its constituents. For example, in this DNA, it is made up of sugar, phosphate backbone, and nitrogenous bases. Now, if someone can see this tire and he gives a deep thinking, and well, eureka, he'll come up with something which probably won't be punctured, like this one. And if we are able to understand, if we are able to visualize the molecules in our body, we may be able to develop something, some better drugs. Now, how exactly we do that? We are doing crystallography. It is a science to understand the properties of crystals in the very basic terms. But in this case, we are specifically focusing on proteins, the crystals of proteins, DNA, and their complex. Now, for time-resolved crystallography, the time-resolved component, we first take protein, grow some crystals, some beautiful crystals, and then we collect the data. Well, not like this, it would look something like this. This data is collected after initiating different time points, different durations of a reaction, and trying to capture each successive stage. Once the data is collected, we analyze the data and come up with beautiful structures. This is the human DNA polymerase beta, and right here is the active site where the actual reaction goes on. Once we zoom into this active site, what we see? Now, this is part of your DNA right here and right here. This is the new incoming nucleotide. You have your metals and water over there. Now, this is the beginning of reactions. Once the reaction starts, you will see something like this. It's a partial reaction. Once the reaction finishes, the reaction is complete. The bond is formed and one bond is broken. This is what I am trying to show you here is just one aspect of what we are able to visualize. Since we have the whole protein structure, we could see what exactly is going on in this environment and everything else. It helps us to visualize the overall mechanism, and by that we can have an idea of how the disease is onset and how it progresses. And as I discussed before, there are direct implications for the structure-based drug design. Thank you.